Hi everyone, in this video I'm going to go through the first example from implicit differentiation, a little bit of the steps that were taken to find the solution and then what that solution actually means. So the question starts, find dy dx, and then they give you an equation, in this case x squared plus y squared equals 1. So what's written just in black here, this is generally how implicit differentiation problems will look when you start. And then all the other work that was with it was my work. So first thing I want to point out is that dy dx means the derivative. It's just that we don't have f of x here, so we can't use the f prime of x notation. So we still mean the derivative, just with slightly different notation. So our steps for these problems will always be the two steps that I've described here. So you'll take the derivative of both sides, and I say it d dx both sides, so take the derivative where x is your input. And then, once you do the derivative, you also have to solve for dy dx, because dy dx will kind of be like mixed up in the equation, but you want your final answer to be dy dx equals this formula. So there's like some algebra at the end. So for most of these problems, you're not going to know, probably off the top of your head, what the graph of this equation looks like. But I really like to start with this one because we actually do know what it looks like, so we can have a little bit of intuition about what is going on and what the answer means here. So x squared plus y squared equals 1 is the equation of the unit circle, which you probably saw in the trig section last semester. So it's a circle centered at 0, 0 with a radius of 1, so it goes out 1 in each direction here. So this image, we don't actually need to answer the problem, but once we do get our answer, we'll come back here and think about how they're connected. Okay, so let's get started. If this equals that, then I know that the derivative of this equals the derivative of that. So this notation that I've put in here, you don't have to do in your work, but it technically is indicating the first steps that we're taking. So we're doing the derivative of each side. Because we're doing this implicitly, kind of with the chain rule trick, we don't have to worry about shuffling our equation around before we start. You can always just kind of dive into the derivative taking. Okay, so on the left-hand side, I have x squared plus y squared. Because they're being added, I can add their derivatives individually. The derivative of x squared is 2x. That's just normal power rule, like 2x to the 1 power. Because x is the input variable here, its derivative kind of goes like we're used to. As opposed to something like y squared, we're going to say, okay, well, if y were the variable, this would be 2y to the 1 power. But because this is with respect to x, I'm going to throw in a times dy dx at the end of that derivative. Technically what we're doing is using the chain rule here, but you may find it easier to think of it as regular derivative with a y in it, and then there's always just a times dy dx at the end if y was the variable. Okay, and then the derivative of 1 is 0 because it's a constant. So we have 2x plus 2y dy dx equals 0. All right, so I've officially accomplished step 1 here. I've taken the derivative of both sides. And now what I need to do is solve for dy dx. This algebra can be a little intimidating, not because it's super complicated, but because it looks super complicated, right? So this looks worse than it's actually going to be. What we actually have is something plus something times what we're solving for. So if we're solving for this dy dx here, I'm going to subtract this term over here. And then I'm going to divide this term on both sides so that dy dx is on its own. So I'll subtract and then I'll divide. Right, so if I subtract 2x from both sides, I get 2y dy dx equals negative 2x. And now I'll divide both sides by 2y. So on the left, I have just plain dy dx equals. And on the right, these 2's will cancel. We'll do this all at once. So I just get negative x over y. So now that I have dy dx equals, this is my final answer. Right? So this is the actual answer to the problem. And I'm labeling it really clearly because just for this one, I want to kind of explore a little bit extra kind of what this answer means. So this is supposed to be a formula for the derivative of this graph at any particular point. So let's go back to, I can't quite fit them in the same screen here, but we'll go back to the image of this graph here. So let's think about some points that are actually on this graph. So this is the unit circle. So right at the very top, that point would be 0, 1. So that means x equals 0 and y equals 1. I can plug those into this formula here. And what I would get is that, give myself a little more space. There we go. So dy dx would equal negative x over y. So in this case, that simplifies to 0. So it's telling me the derivative at that point is 0, which actually makes sense when you look at the graph here. If I was going to draw a tangent line, it would be perfectly horizontal, right? The slope of that line would be 0. So having dy dx equals 0 actually makes complete sense. Let's do a slightly more interesting point. How about exactly halfway through the second quadrant here? So that would be at, I guess, 135 degrees. That point right there, if we think about our sines and cosines, it would be negative root 2 over 2, comma, positive root 2 over 2. So I'm using that just because I happen to know that that's one of the points on the unit circle. So I'm going to take this x and this y and plug them into this formula for dy dx. And what I should get is the slope of the tangent line at that particular location. So if I'm at negative root 2 over 2, root 2 over 2, my dy dx would equal negative x over y. And this looks really, really busy, but notice that on top, these minus signs cancel to a positive, and then I have the exact same thing on the top and bottom. So it simplifies to just 1, which still checks out with the picture. If we come back up here, if I was going to draw a tangent line, kind of squeeze it in here, it would be kind of that tiltiness. And the slope of that line really does look like it could be about 1, right? It's positive, but it's not too steep. That actually makes complete sense as the value of that derivative. If for a different question, instead of just finding dy dx at a particular point, we were asked to find, let's say, the equation of the tangent line at that point. So a tangent line to the curve at, let's use that point we just did, so negative root 2 over 2, root 2 over 2. We would use this as the slope, because that's dy dx at the point, and then this is my x1 and y1. So using this point and this slope, you would put together a line equation in whatever way you like to do that. If you use the formula for a tangent line, that would be y equals m times x minus x1 plus y1. So that would be 1 times x minus negative root 2 over 2 plus root 2 over 2. And of course we could turn this into a plus sign or just kind of leave it as is, unsimplified. So we would have all the tools that we need to do that. The last thing I want to point out before we close is that we needed both the x and the y values of the points to actually compute the derivative at any particular point. And this is the first time that we're seeing that be necessary, right? If we just have f prime of x, then I would say, find the derivative at x equals 2. When you plug in 2 to your formula and you get an answer. But here we needed the x and the y for this formula because it was negative x over y. That actually makes sense in terms of the image, because this image, this circle, isn't a function, right? So if I just tell you the x value of a point, that's not enough information probably, right? There's probably 2 different points that have that x value. So you'd have to specify the x and the y to know exactly where you are and to get, one particular slope value. So it makes sense that when it's implicitly defined, it usually isn't a function. So having dy dx as a function of x and y makes sense because you have to be so specific about the location of the point.